This conference will now be recorded.
Okay, so we are going to be having this like PD, right? PD demo. So you're like joining right now without any kind of basics, directly to the basics. So just for my introduction. Okay, so my introduction is like my name is Rudra. So I'm in this particular industry for nearly 10 years. Okay, and I'm in the complete back end only. Front end I'm not going to be touching, and it's away from me because of more RTL coding stuff and all. Okay, but sometimes we also need to write some kind of small scripts. Okay, TCL, Perl, Python, shell scripting, like that, any of it, you should be able to aware of that. Okay, so now let's say, what is VLSI first of all? Don't give me the full form. What is VLSI? That is full form. What manufacturing? What does a chip contain? Right. So now for that particular, the first terminology we have is IC. That is your integrated chip. So now from earlier days to now on, we are going to be having is like in a smaller area, bigger functionalities. Right. So it is independent of your phone size. Okay. So your chip size is reducing. Okay. And the functionality in that particular chip, we are going to be introducing more and more. So that is what basically in that particular IC, we have different types of, based on the number of transistors we have is SSI, MSI, LSI, VLSI, ULSI, like that, that particular terminology is getting introduced more and more. Okay. So I see you all been aware of it. So I'm not going to be in depth of it. So in this, what you will be requiring to know is like analog and digital related. Okay, so analog, sorry, okay, analog or and digital you will be requiring. So analog basics like manufacturing process, transistor manufacturing process, it might be CMOS manufacturing process, second order effects. All this particular terminologies you will be requiring to clear the fresher level interviews. Or let's say when you want to clear any kind of product interviews, you will be knowing all this particular algorithms. So that will be covered in the basics, and also digital, like conversion of gates, right? So all that particular K map, all that particular stuff you will be able to cover in the digital part. Okay, this will be covered in the basic section first off. And similarly, in the basics itself, you will be also covering coding languages like shell scripting and TCL also, basics. Okay, knowing of certain terminologies, all that will be covered in that particular basics of. Okay, so if you're going for an advanced or let's say fresher level, I suggest is like knowing that particular basics is good. If you are well good enough on that particular analog digital, and you can be able to scope up with respect to Unix environment and also with respect to TCL, then you can be able to join directly to the advanced also. Okay, two levels: basics, advanced. In advanced, we will be purely discussing on the VLSI concepts only. That is like physical design, STA, synthesis. These are the concepts we will be discussing. And also a few concepts related to physical verification. Okay, all this is what we are going to be covering. So now, as VLSI, in this we said is like multiple, or let's say millions, or let's say lakhs to millions, billions of transistors, everything will be introduced in that particular smaller. Though the technology node, everything is changing. That means more number of transistors, everything are introducing. We have just kept a common terminology VLSI. Okay, you know, right? 10 to 100 SSI, 100 to 1000, 10,000, like that. We have that particular terminology difference. So VLSI is not limited, it's a vast. Okay, it's a vast thing. So more functionality we are going to be introducing. Okay, so now in this particular VLSI, you would have heard some concepts called as ASIC and SOC. In your engineering, you would have heard about those terms, right? So what is ASIC? You are going to be developing that particular chip for a particular task, correct? So that means to open the door means it will only open that particular door. So no other functionality will be there for it. So now I want to open that particular door and also I want to scan who is coming in and who is going out. Okay, that means I want one more functionality to be added into it. So that will be coming under SOC. System on chip or silicon on chip, any terms you can be able to state it. So ASIC and SOC. These are the next two terminologies which we will be commonly going to be hearing or using it also. Application specific integrated circuit, and as well as system on chip. So when we are trying to develop this particular VLSI or let's say chip, we should know about that particular process. Okay, so let's say like flow for developing this particular ASIC. This is the major terminology, or let's say this is the flow of any kind of interview also you will be able to know it. Okay, so in this particular ASIC, or let's say when we are talking about VLSI, the major keywords which you need to remember is power, performance, and area. These are the major three keywords which you need when you're trying to manufacture a particular chip. Okay, so for example, you're buying a phone. So what are the key factors you will try to look? Processor, RAM and ROM size. Next, battery backup is also required, right? First focus on this and later on camera resolutions and all that particular features you will try to look into the next. Okay, how many hertz the display is working, all that comes secondary. The first you will try to look into that particular. For me, if I'll take the phone size, right? 6.1 inch, 5.6 inch, like that we have variations. So that area, that means area of chip, okay, which is going to be manufactured. Next is like performance, the processor, that is like in gigahertz. You will be hearing like 2.4 gigahertz, 4 gigahertz, the frequency at which your chip is working. Okay, frequency. And next, power. How much power is required for that particular chip to be working? Okay, let's say dynamic power. Okay, so this keywords, based on this only we are going to be developing. So for this, now as I'm discussing about the flow, the first requirement. Okay, so let me go in this way. How many of you are good at coding? Let's say in your engineering, you would have done some kind of C++ coding and all that, right? So in that, when you're starting up with respect to that coding, what is the first step they will try to ask you to do? Before writing the code, they will ask you to do certain steps, right? What is that? Okay, algorithm, right? So that means like first is your question. They will ask you to write some kind of code, factorial code or anything, correct? So that means first I require is specifications. Okay, for what particular task I need to develop that particular chip. whether it might be opening the door, or whether it can be opening with scanning, or whether it can be a phone processor, anything it can be able to present. Wi-Fi also it can be able to exist. Okay, in any device if you take, VLSI is compulsory, right? That is, your chip is compulsory. Without that particular chip nowadays we don't have any kind of device, right? Electronic devices. So we need that particular chips to be used. So for developing that particular chip, the first requirement is your idea or specifications. So that means the customer who is going to be using it, or let's say, now if you see there are some companies, right? Qualcomm, right? Intel, they are trying to develop this particular chips. That means they are trying to develop that particular chips to do a particular task. The task specifications I needed, right? So first I got that particular specifications. Next comes breaking down that particular specification, right? Algorithm I need. So how many circuits I need internal to that particular developing? How many engineers I need? What is the cost of that particular project? How much can I bid it? All that is done by a team called as architectural designer. Okay, the next is architectural design. So who will try to give all that particular requirements, from where, how many modules I need, okay, how many engineers I need, what will be the cost of that particular project, how can I break down it, how can I reduce the power, everything in that particular kind of block diagram he will try to develop. Okay, so now I have split into the algorithm. From that algorithm, what is the next step? After we written down the algorithm, what we will try to do next? Coding, right? So here comes RTL designers. So they will be able to write the codes in three different languages: .v, VHD, and System Verilog. So they will write down all that particular codes in the behavioral format. Okay. So you know what's a behavioral format? Y equal to A and B, like that we used to write some codes, right? Inside that particular RTL code, module definition, and inside that module we used to write Y equal to A and B, Y equal to A or B, like that we used to write some. So that kind of coding they will try to develop it, RTL designers. Okay, so they will try to instantiate everything, what all is required. They will try to use all that particular stuff. So after RTL designing, what we will try to do? I have developed the code. Now, what is the next step? Run, right? I have to run the code. That means I have to check whether the code whatever I have written is syntaxically correct. First step. And next step is whether the functionality, that is the idea whatever they have provided, it is meeting or not. Okay, the next step is functional verification. In simple terms, after each and every stage you have to remember is like we need some kind of verification. Okay, so the next step is functional verification. So they will be trying to use some kind of test bench codes, or let's say a different ways where they can be able to verify that particular functional verification. Now, as I'm going to be having multiple instantiation, let's say 3 million gates, 10 million gates, like that, we are going to be using. So for writing all that test bench is very difficult. So for that also it is kind of automated. So they will be trying to use some kind of other coding languages to do that particular algorithmic check. Okay, sorry. So now I have tested that particular behavioral code and it is working perfectly fine. With respect to all, now we have written with respect to only logical. Till now we haven't depended on the technology. Okay, we can use this particular files in any technology also. Okay, we can say in simple terms like independent of technology so far. Now next, I have done that particular functional verification. What is my next step? So as I said, I need to know about this power, performance and area. So now here I have written the code with certain modules. So that means internal to that module, I will be having some certain registers also. Yes or no? The registers will be working based on certain clocks, frequencies. So in, let's say like in your device, you have is like certain memory modules, correct? CPU and also let's say camera, network, like that you have different set of modules. Now for each and every module, will the frequency be same or different? Different frequency. So CPU will be faster, correct, compared to every other modules, because that is your heart of your device. If that is working slow, total device is going to be failure. So that means frequency difference. So whoever is developing this RTL code itself, they will itself try to write that particular SDC also. That is your timing constraint. For this module, I need this much amount of frequency. Okay, interfaces delays. So like that certain set of constraints. So all that they will try to write it. Okay, or else based on the complexity of the design, you will also have a separate engineer to develop this timing constraint file. Okay, now next, power. So again, for this all devices, all let's say all modules, will the power requirement be same or different? Different, right? So sometimes I need the camera to be turned on always. Should the camera be turned on always? No, right? Again, in the network module, so when I turn on that particular 4G or 5G network data, will the power requirement will be more or less when it is turned off? So you have phones, right? You are using internet. If that internet is turned off, will the runtime be of your device will be more or less? Turned on, your runtime will be less. If it is turned off, your runtime will be more. So that means based on the requirement also in that network module, my power requirement is changing. So that means different strategies, right? So again, in your laptop or in your phone, you might have some kind of sleep mode, hibernate mode, lock mode, like that you have different modes. So according to that particular mode also, your power requirement will change. So that means again strategies. So all this particular strategies also needs to be developed. So this will be developed by a separate engineer again. So first is timing constraints for your frequency of the frequency of that particular module and all that particular cases. Next, CLP, conformal low power. That means the strategies whatever we have discussed, all that this particular people will be discussing. Okay. Next. So have you in engineering you have heard about some concepts called as stuck at 0, stuck at 1, JTAG, ATPG, like that you have observed? That was actually an optional in engineering. We have it in our subject, but we haven't focused on it much. DFT you would have heard, designed for testability. Okay, so there is actually in our particular concept itself, we have that particular DFT, designed for testability. So that means like once we have developed that particular code, functionally verifying it in the physical, okay, in the physical layout, you will use this particular DFT modeling. Okay, so your DFT will be working parallelly with respect to RTL designs. Okay, DFT again is a separate team. Okay, so first I'll write down the complete flow. After that, again we will go with each and every concept by concept. Okay, what all is required for us, that I will try to go it in a little bit of elaborated way. Now, the next area. Area will be dependent when we are trying to go for physical. Okay, so till now we are always discussing about logical, so we will stuck with respect to non-area dependent. Okay, so we have discussed about timing and power related. After this, so here it's just developing and testing. So CLP developing and testing both will be done. The strategies testing, developing of strategies, everything will be done internal to this CLP itself, confirm a low power. In timing constraints, we are developing those constraints. During the next stages, we will try to use this particular file and verify it. Okay, so till now it will be developed, and in the later stages it will be verified. Okay, and DFT also same way. Once we insert the DFT, then only we can start verifying it. Okay, here they will just insert that particular what logic is required. Those logics will be introduced into that particular netlist. Okay, next, here comes synthesis. Few people will say it as RTL synthesis and few people will say it as synthesis also. So from here onwards, your backend is going to be started. Okay, all the starting steps, whatever we have discussed, till here is your front end. Okay, they will be working on coding, languages, all that particular stuff. Okay, they are working independent of technology nodes. Okay, so only a small modifications and everything they will try to give it to you. If we face any problem also, that means backend engineers, if we face any problem also, we will discuss with RTL designers. Okay, so now after synthesis, your physical design, and intermediate to this, you will also have a stage called as pre-layout STA. Sign off. Next is chip developing, and next post silicon validation. Okay, so this is your ASIC flow. In a brief view, this is about your ASIC flow, and from physical design, it's your backend. We can call this particular stage as our tail sign off. Before synthesis itself, your RTL will be signed off and it will be passed to your synthesis. Okay, and in synthesis, again, some modifications if required, RTL feedbacks, it keeps on going. Our particular process is not always a straight line, it's always in certain loops. Okay, right. So let me go with concept by concept. Yeah, Ganesh. Hello. Ganesh, I think so. You are in mute. Guys, am I audible? Online students.
Yes.
Okay. 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 So now moving forward. So again, when we are talking about idea or specifications, so that means the requirement which you will be getting from the company, or let's say from your designer, is whoever the owns it. They will be providing you what is the functionality of it. Okay, they will just give you the functionality, what will be the area, power requirement, that means how much runtime it should give, how much power it can take, all that kind of specifications they will try to give you, and also the operating frequency of your design, that is your performance. So whenever we are saying operating frequency of the design, the maximum operating frequency is what they will try to provide. Okay, internally you can have different frequencies, but when I look from the overall picture, maximum operating frequency is what you will try to provide it. Okay, internally based on your requirement, you will break down that particular frequency also. Okay, so this idea you will be getting in a raw format. So with respect to this raw format, now architectural designer will try to play a key role. Now I got this particular phone I need to develop. Okay, let's say I want to develop a phone with 5.5 inch. So what all I can be able to implement, whether it is possible or not, whether I can be able to increase it or not. So like that, few steps will be provided by this architectural designer. Okay, the outline is I want to develop a phone width of 5.5 inch. Okay, internal chip size is again they will try to provide you another specification for that. Okay, so next in this particular architectural design, will create outline, of the project. That means from what all modules I need. Okay, as I'm trying to say I need a phone, so what all modules I need for developing a phone, what all modules I need. फोन में क्या क्या मॉड्यूल्स होता है ये में होता है फोन लो. First one is a motherboard is like the complete of all the or ASICs individual. CPU, without CPU nothing is there. As we are talking about a mobile phone, network module. Third one, display module, audio, memory, all this particular stuff you will be able to have it. So that means with respect to this, internal to that particular CPU, let's say, as this plays your frequency generations and everything, so whether PLL, have you heard about PLL? Phase locked loop, correct? Oscillators. So all that whether I have it in my company or should I buy it. Can I develop it or should I buy it? So like that, he will try to check whether few of the modules can be bought or can be used, can be developed. Okay, so here based on the cost of the project, cost, okay, he will try to decide whether to develop it or whether to buy it. So now when you take arm, right, there are certain, again, certain companies, they will try to provide certain macros or memories. Okay, they will already have created it based on your requirement, they will modify it and give it to you. Okay, that means engineer cost is reduced. Instead of that, they will use that particular module n number of times for different projects. They won't give you complete access. Okay, they will give you only a limited access where you can be able to close your design. Okay, you will buy those macros and you will try to use it instead of developing it from the scratch. This makes your work little bit faster. Okay, so like that, certain memories, so you would have heard like SRAMs, right? SRAM, DRAMs. So again, there will be certain other companies which are developing those. So you will try to use those memories in your project. Okay, your task is where to implement as an RTL design. So now this particular architectural designer, for each and every module, he will check what all is required, what all I can develop, what all I can buy. Based on that, he will estimate the cost of this particular project. Okay, and now the bidding process starts. Whenever, if I am also a kind of like a vendor, I'll try to bid it, right? Bidding, you know, right? So that bidding will also happen in our industry. Any industry, if you go, any project, if you are trying to get it, it is always using bidding only. Okay, so that means again, now I'm trying to develop this particular phone, and you're working in a Samsung, and I'm working in service based company. So not all engineers will be from Samsung. So you will try to acquire few engineers from service based industries. Okay, so Samsung employees will also be there, service based employees will also be there. Okay, so again, here also different company biddings will go. So who is providing less cost, they will try to take them. Okay, so like that, our particular industry at each and every stage, bidding is a common thing. Okay, but in real time, when we say bidding is not allowed, internally it can happen. Okay, now, so I have in the architectural design, he will create the outline of the project. So in that particular outline of the project, what all modules are required, how many engineers are required, how many modules I need to buy, and based on that, the cost, everything will be decided by the architectural designer. And he will pass this cost and everything in the format of a PPT, or let's say a structure, and he will present it. Okay, and if that particular company is agreeing, then we will get the project. Deadline also will be provided. Cost of the project get decided, and also the deadline. If we are crossing that particular deadline, we have to pay extra penalty. That will be paid by company, not in our hands. Okay. So, architectural designer will play all this particular key role. That means he will discuss with respect to the internal engineers and also with respect to the main company interface. Okay, we will not directly discuss with respect to that in company. Okay, entire block diagram, yes. So for each and every module, what power will be required, that also kinds of gets decided here itself in this particular outline structures. Okay, so after architectural designer, we have is, what is the next step? RTL designer. So develop the Okay, he will develop the behavioral code in the format of .v vhd system verilog. He will try to have that particular. So based on company, which particular coding, that also will have a change. Okay, few companies use .v, few companies use combination .v .vsd system verilog, few companies uses only .sv. So like that, based on company, they will try to have different coding languages. Okay, so as if you're going for RTL designer, three languages is a must. Okay, next. So in this particular RTL designer, he will design that particular behavioral code with respect to the instantiation. So now I'm buying that particular in CPU module, I'm buying that particular PLL from UIC. I need to develop it or instantiate it. So what is meant by instantiation? Okay, so let's say like I have is I'm trying to develop a 3 input AND gate. Okay, I have already developed 2 input AND gate. As you said, right? A header. In that header, I already have is 2 input AND gate which is already developed. Now by using this particular, okay, by using this particular 2 input AND gate, can I develop this particular 3 input AND gate? Yes, instantiation, right? So let's say all that particular pins will be existing. So we will be having and 2 of dot a1 of a1, like that we will try to write it, right? In this format we will try to instantiate. First one will be the module definition, next will be the name of that particular cell, and next will be that particular in which format you have defined here, the same format we will use it here. So when I buy it also, I need to have this type of instantiations. Okay, from which particular vendor I'm buying, so that vendor in which name they have developed it, I need to have that particular naming over here, such that I can be able to properly link it in the later stages. If there is any small mismatch also, it will be a failure. You need to again remodify your RTL code properly. Okay, so in RTL designer itself, he will try to develop the behavioral code, and also he will try to instantiate properly. Instantiations, same name should not exist. Like that, each and every syntax he will try to maintain properly. Okay, in functional verifications, it's just like testing. So you remember like test bench codes, right? So using that particular test bench codes of algorithm, we will try to test that particular functional verification. So nowadays we are not using test benches. Okay, we have a different format which I'm not aware. As I said, I'm not a front end guy. Okay, just what is what we need to know. Okay, so testing that particular RTL code for any functional failures. So that means whatever the specification is provided and internal to the code, if there is any missing algorithm, that all we need to fix it, and then only we have to process it further. If with that particular failures I process it, what will happen? Total time waste. money waste, all that will happen. So that's why we need to have that particular certain pass ticks available. Okay, if that pass ticks are not available, the next stage engineer will not accept your design. He will just throw it back to you with certain scoldings. Okay, stage to stage this happens, seniority level wise also it happens. Okay, now after functional verification we have is timing constraints, CLP, and also DFT. So in timing constraints, so this we have a term called as STA engineer, we will say it. Okay, STA engineers. So this concept also we will be able to discuss in our particular flow. We require it. Okay, so it will be going in detail. Okay, timing constraints will be in detail in the advanced classes. So in this, what will be the frequency of your clock, of your design? That means types of clocks, and also we will be discussing about interface delays, how the cell delays are getting calculated. So like this, we will be having multiple terminologies which we are going to be discussing in STA. Okay, timing paths, timing arcs. Okay, all this will be discussed in STA. So next is CLP. So this concept will also be covered. That means what is required for us, that level we will be covering it. Because from this conformal low power or low power strategies, we will be having multiple interview questions. And also based on this, our design will slightly change. So that's why this concept is a must. Okay, you should know this, what is CLP is. Okay, what is actually done in CLP, that you will be aware of it. What needs to be modified in the CLP, that you will not do it. That will be handled by a separate engineer. Yeah. Any questions? No. Online, I was hearing some noises, so that's why. Okay. In conformal low power, we will be hearing terms like power domains, voltage domains, strategies. This you might not use it right now. SPA, set port attribute, and look, power state table. So like this, concepts we will be discussing in this particular duration. That is like what are power domain strategies and power state tables. All this we will be discussing in the advanced classes. STA, again I'm saying STA will be going in detail. Pre-layout STA, post-layout STA. Both will be covered. So how to develop that particular constraints. That also we will try to give you guidelines that you need to develop. Okay, until and unless you ask questions, we will not touch that. We will guide you. Okay, you have to do it. We will provide you all that files, but again parallelly you need to develop your own understanding. Whatever we teach it, we will ask you to develop parallelly. Okay, until and unless you develop, you will not know that particular concept, I'll be frank. Okay, so next is like CLP, that we don't have a developing process, that we will provide you, that you will modify it and you can be able to learn it. Okay, seeing that particular errors, we will ask you to modify it, see the errors and make some adjustments accordingly. Okay, next, after CLP, DFT. DFT is again a separate course designed for testability. This is again a vast topic. This will not be covered easily because based on the project, right? Whether JTAG or BIST algorithm, In BIST itself, LBIST, MBIST, like that, we have different BIST algorithms. Which algorithm to be introduced? All that will be varying. Okay, and according to that, or let's say according to your design, there will be a concept called as scanching. Okay, so in this particular DFT module will be inserted in RTL. That means if you are using JTAG module will be introduced. If you are using BIST module will be introduced. Modifications in the RTL itself. Okay, the first step is modifications in the RTL. Next, we will be having a file called as scansetup.tk. So, which we will be requiring it in the synthesis stage, where you will be knowing about a concept called as scanching, and also frequency of that particular module, that also gets decided. Let's say timing constraints, instead of saying frequency, timing constraints for DFT, that also will be present, and also the required ports will be provided in this particular scan setup.tk. Okay, so in this DFT purpose, or let's say DFT side, we will be knowing what is scan chain, how do we get scan chain failures. That is the concept we will discuss. Okay, this will be discussed during synthesis as well as in your placement stage. In these two stages, we will be having more focus on this particular scan chain testing. Okay, now after DFT, we have is synthesis. So synthesis is having a separate flow, or let's say from this particular stage onwards, your complete PD will be, or let's say your course will be started. Okay, STA is one concept, and you will be having from synthesis, PD, sign off. These three concepts also will be discussed. Okay, so let me go in a separate tab. Okay, so now from this particular stage onwards, your course is going to be started. So synthesis. So always remember, whenever you are learning or anything, yeah, okay, first algorithm, or let's say first concept should be known is like goal. Okay, and also what is the purpose of it, and next what all the required inputs, and what is the procedure, and next output files, and next should be the what checks should be done. So at any stage if you go, you should be knowing this. Why should I do it? What happens if I don't do it? Okay, that kind of algorithm knowledge you should be able to get it. Okay, any concept you should understand is like, why should I do it? Okay, so now, till now, all the information we have is in behavioral format or gate level format. Behavioral format, right? With respect to that behavioral format, we cannot develop a chip. Okay, it becomes very, very complex. So we cannot be able to develop. So any information I need to have it in the transistor level. Then only I can be able to develop it. So that's what we are going to be saying is like a gate level. Okay. So our major goal of this particular synthesis is to convert the RTL to behavioral code. So internal to this, it will also perform that goes in procedure. So internal to this, your optimization, all the three terminologies which we discussed in the starting, PPA, power performance area, that will be optimized. Okay, power performance area optimization will be started from your synthesis stage onwards. So that means all the checks related to your power performance will be started from here. Area from your physical design. Okay, you will check area here also, but majorly you will check it from your synthesis. Yes, RTL will have the behavioral code format. Register transistor logic, RTL full form. Okay, so what is the purpose of it? So the purpose and goal here is same to same. That means I need to convert that particular RTL code to behavioral code and have that particular equivalent DFT modules inserted, or let's say scan chains inserted. Okay, such that it will be helpful for your physical design. Okay, if we don't convert it properly, your physical design will throw multiple failures, or let's say that particular tool will not support your behavioral code. Okay, no backend tools, that is your physical design tool, supports your front end format. To be specific, your behavioral code format is not supportable by the physical design tools, so it will fail there. Okay, so that's why we need to check it properly and then we need to pass it. Yes, so as it's an RTL code, that is, sorry, my bad, to gate level. Thanks. Okay, your RTL code should be converted to your gate level netlist. My bad. Earlier I given the correct explanation while writing, I've written it wrong. Okay, so without that particular gate level format, you cannot be able to develop it. So indirectly, our major goal is to technology independent to technology dependent. So your RTL is technology independent and your gate level netlist is a technology dependent. Okay. So here purpose is same. So that's why I'm not writing it separately. Okay. Now you have worked on in engineering during your VLSI labs. You would have done Xilinx tools and everything, right? FPGA and all. So you have provided some files as input to that particular tool, correct? To Xilinx and everything, you would have provided some inputs such that the code will be run and it will be provided in the FPGA. So what are the input files you have provided over there? For that particular Xilinx tool, what is the input file you have provided? You have created a file. In which format you have created that file? .v only, na? .v, .vg, .vhdl, any format, whichever you are trying to develop, in that particular format you have created it, opened it, saved it, run it there itself, correct? So that means the .v file is an input to get that particular required output, correct? After that you will be having some kind of graphs and everything, correct, where you will be seeing the clock diagrams, how that particular data is present, all that you would have observed, yes or no, simulations and everything. So similarly here we are not going to be seeing any kind of simulations, but we will try to do it everything using the report format only. Okay, so the input, as we discussed, the first input required is RTL file. Next, so as I said, we are going to be optimizing our design with respect to PPA. You will be passing timing constraint file in the format of SDC or MCMMVC, multi-corner multi-mode. SDC is synopsis design constraints. So timing, power, CLP, or let's say to be specific, UPF file you will be passing, unified power format. So this file we will be studying in detail during the advanced. Okay. Next, area related. Okay. So based on the type of synthesis which you are going to be using, you will be getting the area information from using a file called as floorplan.def. Okay, based on the type of synthesis which you are going to be providing, the area information is provided using floorplan.def. Okay, next is like I want to convert technology independent to technology dependent, and also I want to convert RTL to gate level netlist. The gate level, okay, so
Hello, sir.
what
You are
I'm
not audible, sir.
I think so my network got disconnected in between. Am I
Okay,
audible
okay.
now?
Yeah, you are audible now.
Okay,
Thank you.
perfect. Okay, so as I was trying to say, I need that particular gate level information. So gates, whenever we are saying gates, I want is like standard cells. So standard cells are basically your AND gate, OR gate, combinational circuits and sequential circuits combined. Okay, so that we will call it as standard cells. Okay, a simplex circuits we will call it as standard cell. Complex circuits we will be calling it as macros or memories or IPs. Any terminologies we will be able to state it. Okay, so that standard cells are already developed by analog design engineers. Okay, analog design engineers play a role with respect to the stick diagrams. You know stick diagrams, right? Internal like L shape, U shape, everything. So those particular internal to that particular gate transistor level will be performed by analog design engineers. We are not going to be working purely with transistor level. We are going to be playing with metals. Okay, internal structure information we will not touch. Okay, transistor level we are not going to be working. Again, I'm stating. Okay, which is already developed by analog design engineers, and we will use those particular information in our design. Okay, as that particular circuits are already developed, that means the shape information, timing information, everything they will try to provide it in the format of .lib. We will state it as logical library or liberty file, where it will be having the timing, power, and area information of standard cells or macros which we are getting it. Okay. Now, the next is dot left physical library or layout exchange format where it contains the shape of the cells. So under which shape that particular cell is structurized, that information will have. Shape of the pin it will have. Okay, so like that we will be having multiple terminologies internal to this left file. Okay, and next information we will be having is technology file, which will be developed based on the technology node which we are using. How many number of metals we are going to be, okay, how many metals we are going to be using, and what is the spacing between the metals, what is the minimum area, there will be certain rules. All this will be present in this particular technology file. Okay, so this lib and left will be provided by vendors. So when I'm saying vendors, that means from where you're getting the standard cells and macros will be provided by vendors, which will be having standard cell and macro or mem or IP. Any term you can be able to use it. And this technology file is provided by vendors, sorry, Foundry.
Hello.
Yeah,
Sir, what is vendor here?
from where you're buying that particular cells information. As I said in the
Okay.
starting, right? PLL, someone has
Any
developed it.
example of this vendor? Like you can give
ARM,
like
Synopsys,
micron. Yeah, okay.
yes.
Got it.
Microchips, ARMs, everything. They will be able
Okay,
to
okay,
provide you this.
okay.
Okay, so technology file will be provided by Foundry. So under which particular Foundry you're working, the equivalent technology file you're going to be using. So let's say for example TSMC. Okay, that is one of a foundry, Intel. So like that you will be having multiple global foundries, like that you will be having multiple foundry. So they will provide you that particular equivalent technology file, and you are going to be using that technology file for your processing. Okay, so mostly company to company we will not see a big change, but the format which they will have a support will have a change. That is the difference we will be able to find. Okay, so and one more file, TLUP, parasitics information, table lookup for parasitics visit. Okay, table lookup for parasitics, so which will be having your, based on the technology node, resistance, capacitance, inductance information will be present. Okay, so these are certain set of files, and again when we go into that particular flow, if we need to add anything we will add more files based on the requirement. As I said, from the DFT scan setup.tcl, so like that any other extra files if we want to add it, we will be adding those particular files. Okay, modifying certain things, like that we will try to perform it over here. Okay, so during the course, we will go into, or let's say, we will make you to open each and every file and make you understand what format it looks. Okay,
Sir,
we'll just
I do have
hmm,
one query, sir.
right.
So vendors are designing basically the standard cells and macros. So that is not the technology dependent files, or they do follow some technology dependent rules that foundries are providing. Means my question is, dot lib files are totally technology dependent or independent?
So for each and every technology, this lib and left will be developed. Technology dependent.
It must follow some rules that has been provided by foundry. So based on that, they are designing standard cells.
Yes.
Okay, okay.
Okay, so under which particular technology we want to work, we have to pick up the equivalent standard cell library and left files accordingly. Same goes for your macro also.
That means it's based on the PDKs, right, sir? The foundries that they are is providing, or it's supposed to be dependent on that particular PDK.
Uh, yes, so
Okay.
PDK we can say is like for each and every technology you are going to be having separate PDKs.
Yes, yes, sir. Yes, sir.
So it's like a compressed format of your libs and everything. PDKs we
Ye-
will say. Okay,
Okay,
so
so
let's say for
dot lib
example,
file will be dependent on a specific PDK actually, right, sir?
yes, correct.
Okay, okay.
Okay, so PDKs are like your compressed information of your all the libraries which you are going to be using for your designs. Libraries, left files, technology file, all that you will be able to find it. Okay, so again, certain PDKs you will be getting from vendors. So whatever the technology we are developing, it should map properly with respect to the technology whatever they have used. If there is a mismatch, the developing will fail. Okay, it will not work properly. So whatever the technology, if I'm using 14 nm, I should pick up the equivalent lib and left from that particular 14 nm libraries only. If I use 28 nm or 7 nm or any other case, everything will be a mismatch which will not work properly. So that's why for each and every technology node, the equivalent libraries, left files, all that particular information has to be structurized again and again. Okay, right. So now the next step is procedure. So it is basically of 3 steps only. Okay, so I will not go in elaborate of this. I'll just give out the terminologies. During the advanced classes, we will be having more and more. Analyze, elaborate, and compile. Okay, so when we have is basically, or let's say majorly of this particular 3 different steps for the synthesis flow. Okay, if we execute this, your synthesis is done. But whether the optimization is as per my requirement or not, if it is not proper, how do I make it more optimized? That is what we have to do it. Okay, so as I said, right, we are going to be performing the optimizations. So optimizations will be happening in this particular compile stage for your power, timing, and area. All this gets optimized in this particular compile stage only. Okay, so whether this particular output, okay, that means during this particular check, when the result is not as per my expectation, then we have to re-optimize, make that effortness more by adding certain fixes. That's what we need to play a role over there in the synthesis. Okay, synthesis is the very much faster stage. Okay, so our major task is first one, RTL is converted properly to gate level or not, and the timing results, power results are per expected or not. That is what we need to check. If it is as per expected, then we will directly pass it to your PD engineer. Okay, so then the PD engineer will start processing. He will start with respect to the physical layout. Till this particular stage, you cannot see the physical view of your design. Okay, in synthesis everything is logical, or let's say virtual. To be specific, all the optimization, all the views will be virtual only, you cannot be able to see it. Okay, so now the next is output files, so which will be passed to the next stages, or which will be used for your analysis only. Okay, what all inputs we have provided, similar output files we will try to extract it. This extracted files will be in the format of your gate level. All the input files we have provided is with respect to RTL, let's say. Now the output files will be extracted with respect to your gate level format. That means with respect to the proper instantiation, mapping and everything, you will be finding this particular files. Okay, so first one will be your gate level netlist. According to the company, the extension will change. .v, .vg, anything you will be able to find it. Okay, next is timing constraint file. Again, I'm saying few files will be used for the next stages and few files will be restricted. UPF. Okay. Next is sanity checks. So that means what all inputs we have provided, okay, and the outputs which we are trying to extract, whether it is proper or not. Okay, what all checks we need to do, the commands execution and everything we will discuss it during the post. Okay, that is during the advanced classes we will try to discuss it. Okay, so few hints I have to keep it as it is. So in that one of an hint is this. Okay, during the classes we will discuss how we are going to be verifying it, how can we able to fix it, all that we will discuss it during that particular synthesis sessions. Okay, next, after synthesis, pre-layer testing I'll touch it later. Okay, so next we have is physical design. Okay, so before going to physical design, let's take a short break. 15 minutes we'll take a break and then we will be back. Okay, 3:30 we will be back. Continuous also we will face Okay. Online students back from break. Okay. So, okay. So, in physical design, so this is the stage where your physical layout is going to be started. Okay, we are going to be using CAD tools only. Okay, 2D algorithm CAD tools only we are going to be using it. Our particular design, or let's say chip, is going to be manufactured in 3D, but still we are going to be using only 2D algorithmic based tools only we are going to be using it. Okay, so physical design, our goal is to what all logic we have that should be implemented in the physical layout in the given area, such that your timing, power, area, everything will be satisfied. Okay, or let's say will be met. Okay, so now what are the inputs required for performing physical design? We will be having similar inputs whatever we have provided for your synthesis. Similar inputs will be provided for your physical design also, but all the inputs will be with respect to the gate level format. Okay, your lib left technology file, that will be common. Okay, TLP, all this will be common. Your scan-def file, gate level netlist, SDC file, all this will be with respect to your gate level format. Okay, because in your physical design, the tools will not support behavioral format. Okay, so that's why you will be having is like all the gate level information files, gate level netlist, SDC. Let's keep it like major. We will use is only MCMM, which contains of multiple SDCs and everything. Scandef dot tf dot upf dot ndm dot left dot lib tlup or nxtgrt. Okay, these are all the set of inputs which you are going to be providing it for your physical design. So next is like procedure. So for this particular physical design, it will be the same as your synthesis also. It runs in 3 stages synthesis. Here it will be running in 5 stages. Okay, floor plan, power plan, placement, CTS, routing. Okay, so this will be the total 5 stages available for the physical design: floor plan, power plan, okay. To be specifying, actually there is also one more stage. Based on the level of the design which you are going to be working, there will be one more stage prior to the floor plan. Design planning. Okay. Before this particular floor plan stage, you will be having a stage called as import design or design planning, where each and every block, okay, each and every block area will be decided. Okay, the shape area will be decided in this particular design planning stage. So to get an understanding of this, the first information you need to know is type of design structure. So we have is basically two types of design: flat level designing and then hierarchical designing. Okay, flat level design and an hierarchical design. So flat level design represents RTL to sign off single engineer is going to be performing. Okay, that means from your synthesis to the post layout, completion of the chip will be done by a single engineer. There will be no partitions. Okay, a complete structure is decided by one engineer, is completed, not designed, is completed by one engineer, flat level design. So when we are talking about hierarchical design, okay, that means your design is going to be split into multiple partitions and requirement of multiple engineers. Okay, RTL to sign off will be taken with the help of multiple partitions for hierarchical design. Okay, so when you're trying to perform flat level design, your flow will be having import design, floor plan, power plan, placement, CTS, and routing. When you're trying to do hierarchical design, you will perform first is import design, after that design planning, floor plan, placement, CTS, routing. All that steps will be happening. Okay, so in this particular design planning stage, will be done by SOC level engineer. What he will try to do is he will partition the complete SOC into small blocks according to the shape which he requires. He will try to factorize it and give it to separate engineers. Okay, so based on the module splitting, he will decide that particular shape and size of the block, and he will pass this information to the block level, or let's say partitions. As we were discussing earlier also, CPU is done by one person. So for that, what is the shape and size of that particular CPU? That will be handled to him. Okay, and where it is located, that kind of information he will be able to get it. Next, memory module. So like that, network module, audio module. So each and every module will be split into separate partitions. Based on the complexity, you might handle 2 to 3 blocks also, sometimes 4 5, because some certain blocks will be smaller. Memory is a smaller one, so you can combine it with respect to other partitions. Okay, so like that, based on the complexity of the design, you, an engineer, can hold up to 5 to 6 blocks also. Okay, or sometimes even though he is a 10 years experienced guy, he will handle only one block, which will be a complex block. Okay, so like that, based on the criticality, he will try to split it and give it to individual engineers. Okay, so that is what happens in the design planning stage. Okay, next is like floor plan. So, how many of you have are aware of civil engineering? What they will do? You know, right? Civil engineers, what they will do. So, we are like civil engineers only. They work in hot suns and we work in uh, cold ACs. This is the biggest difference. And they work with mud and sand and everything, cements. We work only with computers. Okay, this is the kind of differences we are going to be having with them. So that means when I'm constructing this particular module, for example, CPU module, in this particular floor plan stage, the first factor of placement goes with respect to the macros, where I need to place them, such that they will be able to have the enough power to be activated. Okay. So in this particular floor plan stage, from the term itself, we can be able to state is we are going to be planning the floor. That means we are planning the design in such a way that your macros will be placed properly, or let's say effectively utilizing the area such that your standard cells will be placed without any congestion. Okay. In floor plan stage, placing the ports. So again, this, let me go with step by step. Floor plan. In this particular floor plan, we will be having again a series of steps going to be processing. So creating of core area and die area. And next is placing the ports, placing the macros, okay. After each and every stage from now onwards, again you will be having stage by stage verification. Okay, yeah, some kind of like a blueprint, yes. But here your standard cells will not be placed. Okay, only the macros, that is your IPs, memories, only that particular complex design circuits only will be placed here. Okay, the standard cells, that is your gates and your sequential elements, will not be placed in this particular floor plan stage. Okay, so now here, as I was taking the term die area and core area. So die area is your chip area. That means the outer line of that particular design. Okay, outer line of your design will be that particular die boundary. And internal is your core boundary. And internal to this particular core boundary only, all the cells will be placed. Okay, your standard cells, your macros, everything should be placed internal to this particular core boundary, because for each and every placement we have certain rules. Those rules are created internal to the core boundary only. So that's why we need to place those particular objects inside that particular core boundary. And in between this tie boundary and core boundary, you have is IO clearance, where you're going to be placing the interface objects, that is your ports, pads, all that will be placed in that particular IO clearance area. Okay. So for this, what all guidelines are there, how we are going to be placing it, all that theory and practical both will be covered. Okay, how we are going to be placing the macros. Okay, what will be the goal of the floor plan stage. Everything we will be able to see pin to pin connection based, and we will try to place that particular macros properly. Okay, such that you will be having your standard cell placement easy. If this particular floor plan is bad, consider that your design will never be closed. If floor plan is good, within 2 iterations or 3 iterations, you can close the design. Okay. If your floor plan is bad, after routing stage also you will come back to the floor plan, you will modify it and again you will process it. So that's why this particular floor plan will be closed in around 10 to 15, sorry, max of 10 iterations. That is the macro placement, everything should be closed in 10 iterations. Okay, by redoing that particular till certain stages, seeing the violations, redo the floor plan, this iteration will keep on going. Again, it's not a single iteration. Okay, so next is power plan. Okay, in power plan, we are going to do what? Distribution of power. Okay, so based on that particular power domain, or let's say voltage domain, where which particular power net has to be passed, how it has to be passed, all that we have to take care. So here, distributing the power such that you will be facing less IR and EM violations, less IR drops, you can say. For this, you will be having terminologies support like rings, straps, rails, bumps. Like this, you will be hearing some keywords. Okay, so now how that particular distribution we can be able to. Okay, here power plan we will just source the script. We are not going to do that particular strategy depending. Okay, because this particular wire, so basically when we are seeing this particular external wires, right, the width of the wire is different from the internal wire, correct, for that particular power transmission. On what basis that particular width is changing? Why external width is more and internal wire width is less for the power transmissions? Voltage. So that means in alternative terms, I'll say is like current density. Current density passing through that particular wires is also different. Majorly because of that, you will be having that particular width difference. Okay. Next case, from one wire to another wire, we are having that particular spacing also, right? We that particular spacing is not followed properly. What will happen? Shorts, right? So that all in mind, I have to decide this particular distributing the power also properly. The width of the wire I need to decide, the spacing between the wires I need to decide. So in that particular area, if I have more number of houses, according to that the power lines has to be more, right? If there is less, voltage drops you will fix. So like that I have to focus on all that algorithms and I need to design that particular strategy properly. So that means it is taking more time. So that's why, as a PD engineer, you will not focus on developing that particular power planning. You will just source it. If you face any issue, then you will discuss with respect to that particular power team and you will get it fixed. There is a separate flow. Okay, to have all this particular strategy checking, you will use another tool called as redoc. For power related, that is EMIR, all that you will use a separate tool called as redoc tool. Okay, from that particular results you will analyze it and you will try to fix that particular violations. Okay, so Next is placement stage. So you're going to be placing the standard cells based on timing and less congestion. We can say types or procedure, post placement, legalized placement, and detailed placement. So again, this is the stage where your actual optimization is going to be started. Okay, so before this particular placement stage, you should know about STA certain concepts. How your timing is getting calculated. That is your setup slack, setup time, hold time. So like that, we have certain STA concepts. So all that particular STA concepts has to be covered before this placement stage. Otherwise, you will not be able to get the concepts clearly. How I can be able to fix it? How can I be able to get that particular transition time in control? All that you will be able to understand when you know that particular STA concepts. So that's why what they will try to do is, or let's say what we will try to do is, before this particular placement stage itself, we will try to have either STA hours continuously or parallelly STA and PD. Okay, I'll mostly go with respect to STA and PD parallelly, and if required, I'll take STA hours continuously. That's how I will try to go with, such that you will not be backward in theory, and sometimes what happens is like your practical will be moving forward and theory will be backward. To not face that particular difficulty, we will certain go in parallel things. Okay, and here also after each and every stage there are certain compulsory checks which you need to do it. If you don't do that particular checks and in the later stages you find it, then it will be very much difficult for you to fix it. Okay, so that's why prioritization of checks and fixes is your priority. In simple terms, when you go to industry, right, it's a push button flow. Okay, if you just click or execute one command, the flow will be executed. Then what is the purpose of us? To analyze it and fix it and make the results according to our particular standards. Okay, so if that also tool is done right, then there is no work for us. Okay, so where we need to place it, how we can be able to fix it, that is what our priority is. So for that, you will again do multiple iterations, placing one type of fix in one iteration, parallelly providing another, which gives better result, that you will proceed forward. Okay, next is CTS stage. In CTS stage, your clock tree. Okay, in CTS stage, your clock will be propagated and clock tree will be formed. Okay, clock tree. So when we are okay, so when we are discussing about our sequential elements, the clock should be reaching faster or slower. If our particular design should be working properly, the clocks reaching to that particular sequential elements should be faster or slower. Neutral. No neutrals here, either fast or slow. If the clock is reaching in a neutral or slower phase, that means the sequential element which I want to work at certain duration, it will not work, right? I want that particular clocks to be reaching there faster. Okay, and whether, okay, there is a case where clock reaching to multiple sequential elements at the same time is allowed or not. It's not allowed.
It's allowed.
Clock reaching to multiple sequential elements at the same time is not allowed. So the reason why, we will discuss it, okay, during the STA. Okay, there is a term called as skew. This skew value cannot be equal to 0, but it can be nearly equal to 0, but it cannot be equal to 0. That means a small fractional change between the clock reaching times should exist. Why? This type of questions and answers we will try to discuss. Okay, parallelly, what we will try to do is like some concepts will give it for you as an assignment. Okay, that you, until and unless you come back with the answers, we will not discuss. Okay, because we want is like interactive basis. Okay, we also want to know whether you are able to understand it and do it from your, you are able to analyze it. That's what we are going to be testing it. Okay, so because in industry we don't want mug up guys, to be frank. We want is the persons who can be able to analyze properly. Okay, the where is the problem and how can we fix it, this is what we look. Okay, we don't want someone's footstep following. So that's why we will, as much as possible, we will try to explain things and we will ask you itself to do it. If you face difficulty, we have dedicated mentors, they will be able to support you face to face. Okay, so that's why don't feel discomfort, you can be able to 24/7, you will be getting a support. Okay, so next, here clock tree will be formed, and during this particular clock tree formation, as I said, right, this particular skew type of violations. Okay, if any kind of targets violations, all that we will try to analyze it and fix it. If the clock is reaching late, why it is reaching late? How can I reduce it? Different types of clock trees. All that we will be discussing during the CTS stage. Okay, how can I make the balanced clock tree? All this we will be having multiple key terminologies. Okay, all that we will be discussing. So parallelly you will be hearing about crosstalk, EM, and all that with respect to clock path also. That how we can be able to fix it, the rules specifying, all that will be discussed. And from here there will be one more file called as spec file, specification file. So this is the major file in CTS, cts.spec. That is of the one of the major input interview question also. What does it contain? How we can be able to modify it? How we can add more features? That is what we will be discussing. Okay. And the next is routing. If you get routing, consider that your course is almost done or your project is almost done. That means your task is reduced, your burden is reduced. Till CTS stage, that means to be exact, from placement to CTS stage is what your major headache is. Okay, so once you get into routing, physical routing is happening. All the nets, that is your signal and clock, will be physically routed. During your power plant stage itself, your power and ground will be routed. And during this particular routing stage, you will be having virtual connections into physical formats. That means your metals will be created in this particular stage only. Okay. So this concludes your physical design. Okay, it's kind of a very brief view. So in your course duration we will go in very much detail as much as possible, each and every sanity check, from our particular trainer side and mentor side we will try to display it as much as possible. Okay, If trainer gets enough time, he will try to display you more and more tool bases also. Okay, parallelly you can explore that in your lab view also. Okay, when you get working on labs, you will explore each and every option. Okay, there is no control on it. You have the full access to that particular tool. Okay, until and unless you feel I'm enough, till that time you can be able to access that. Okay, so the next stage is sign off. So in this particular sign off stage, you will be having physical verification, STA, or let's say timing closure, functional verification, let's say in simple LEC, and next power. So like this, you will be having multiple sign off checks. So because after this sign off, it directly goes to the fabrication. Okay, so before going into fabrication, as much as possible, we will try to verify every step by step. Okay, because fabrication is costly. Because of some failure in a sign off check, or let's say if we have missed it during fabrication, if it is failed, again they will try to, your cost is going to be cut down. Okay, so that's why we have to be very careful in this particular sign off stages, or let's say tape out stage, we will be able to say it, where you will get a sleepless nights. Okay, that will be around like 1 month or 2 months only. Okay, so very crucial stage of our particular VLSI. Logical equivalence check. It's kind of like your functional only. Okay, so now in this particular physical verification stage, you will check for the metal densities and all the technology rules, whatever we have specified for that particular metal, whether it is followed properly or not. Okay, that is like your width, spacing, cross width, spacing, and also with respect to that particular metal densities, whether we can insert any kind of metals, all that will be checked in this particular physical verification stage. Okay, in simple say density and your min width, min spacing, area. Majorly it consists of this particular categories, but internal to this we will be having step by step multiple other categories. Okay, for those who are going to work as physical verification, they no need to worry about any kind of timing related. They will just clear the DRCs and LVS. These three terms comes under physical DRCs, design rule checks, and these two terms comes under LVS, layout versus schematic. Okay, in timing closure, you will try to check for crosstalk, or setup and hold slack, DRVs, and there are multiple more. Okay, inside crosstalk we have crosstalk noise, crosstalk delay. So like that we will be having variations. So all this we need to get it fixed. Okay, it will be going like an ECO cycles, engineering change orders. Okay, so next is functionality. LEC is functionality check. We can also say it as data to data check. And next, internal to the power, you will be checking for IR and EM, and also you will be checking for leakage power, dynamic power, all that particular cases. If everything is clean, we will close it and it goes for fabrication. If it is not clean, we will fix it and pass that particular fixes to the routed database. Okay, here physical verification is done by a separate engineer, STA separate engineer. Okay, and LEC, it will be run in the flow itself. Okay, no major. If required, a separate engineer can be kept. Okay, so like that each and every check will be done by separate engineers. If physical design engineer itself is good enough, then he will run everything. Okay, if required, I'll take multiple engineers. So based on the requirement, we will be having this separate engineers. So if I'm a PD engineer, I know STA, I'm not aware of physical verification, then physical verification engineer will be called in. Okay, there will be a requirement. So like that, based on that particular knowledge, knowing, you will be having that particular task assigned equivalently. Okay, so now in this particular timing closure, this whatever we are discussing is with respect to the post layout STA, right? So similarly, I written one more term called as pre layout STA. So where your timing constraints will be checked and closed. In pre layout STA, your timing constraints will be checked. In post layout STA, total design timing will be checked and closed. Okay, with respect to what all constraints we have closed in pre-layout STA, only that will be used for your physical design and also for your post-layout STA. And after that, it goes for chip fabrication, and after that you will be having is post-silicon validation. So in that particular post-silicon validation, they will cross verify again. Okay, they will cross verify all the checks with respect to the fabricated IC. Okay, functionality and timing check on the IC will be performed. If it is failing by a bigger, he cannot be able to fix it. So in this particular post silicon validation, few of the fixers they will be able to do it manually. Okay, few fixers they will be able to do it manually. Few fixers they will not be able to do it. Then they will send a feedback to the PD engineers. Okay, to our particular team they will pass it, and we have to reiterate it, fix it, and provide it. Version 1, version 2, version 3. Like that, we are getting different versions, right? This is the reason. From version to version, we will be having small functionality enhancements and also the fabrication issues getting fixed. This is what is happening in the industry. Okay, we are almost using all the constructed only, but we are enhancing more and more features into it. Okay, clear? So this is all about the demo of this particular course. Okay, so we will be discussing about basic fixes of all this except for density, timing closure, everything we will be fixing it. Okay, we will do one or two iterations of ECO in your labs. Physical design, everything will be done in detail. Synthesis will be done in detail. And in ASIC flow, you will be knowing about what is CLP, what is scan chain, and how we can reorder it, and STA. All these concepts we will be doing it in our course. And the tools we have is synopsis and cadence. For physical design, you're going to be using is ICC2 in the labs. If you have from the cadence side, you if you have done it, you will be getting is like Innovus. And for synthesis, you will be using is DC. For timing, you will be using is prime time. This is with respect to the synopsis, and with respect to cadence, you will be having Innovus, Genus, and Tempus. I'm not sure about this particular Tempus part, but Innovus and Genus you will be having. Okay, Saturday and Sunday will be your theory, and Monday to Friday, or let's say Monday to Thursday, will be your labs. Okay, theory point will be handled by trainers who are trained, let's say experienced. Okay, mentors will be handled by juniors to them. Okay, they are also experienced, but they will be dedicated to teaching. Uh, so according to the enrollment which you are going to be doing, based on that you will be accessing both the tools. By default, you will be getting access to Synopsys tools. Based on the enrollment, you will be getting access to the Cadence also. Okay, if you guys have any questions, you can shoot it because I'm done. Yeah, give him everything will be handled during your labs only. Yeah, the e-learning mode also you can be able to access both the tools. Again, I'm saying it's based on the enrollment which you're going to be doing it. E-learning will have the recorded sessions only. Okay, any doubts, doubt session will be provided, doubt clarifications and everything. They will be having a sessions for that, but you will may not be able to attend to that particular theory sessions. Okay, GVM sessions, that's Unix, everything will be done during your labs part. Okay, basics you will be touching in the initial itself, and everything you will be done. So enrollment means like during that particular confirmation, right? Whenever you say that I'm going to be joining the course, I want is like both the tools or single tool. Cost, according to your cost, how much you can be able to afford. Based on that you can be able to decide. Okay, so once you enroll it to the, this is like a demo session. Once you enroll to this, so daily you will be having 3 hours, Monday to Thursday, 3 to 4 hours, based on that particular phase which you are going. It can be certain, mostly it's 3 hours only. So if you want to close it, or let's say if you slow down, so we might take is like 4 hours certain times. Okay, theory will be only Saturday, Sunday. Mostly it will be from 10 to 1 or 9 to 12, 3 hours. Saturday 3 hours, Sunday 3 hours. Same timings. Okay, Monday to Thursday, it will be either morning half or second half. It's based on the availability of the mentor. Okay, any other doubts? Daily 3 hours. Let's keep it like daily 3 to 4 hours. You will be having is like lab sessions Monday to Thursday.
Hi, for e-learning online course, lab sessions, how we can do?
So as how you have attended right now, right? Go through this particular go to link. So the
Okay.
same way you will be able to access it, and the tool you will be getting VPNs and everything. So you will be able to connect to that VPN, and you will be able to connect to that particular tools.
So at the time, mentors will be available.
Yes.
Yeah. Okay. Thank you.
Yeah. Welcome. So yeah,
So
you
from
can.
from the very first day, can we get access to the tools?
Yes.
Okay, but it was said that 24 cross 7 means this is the duration by which we can access the tool, but it is that like that only 3 hours on from Monday to Thursday we can have access, right, sir?
No, Monday to Thursday, 3 hours dedicated mentor training session will happen.
Okay,
But you
okay.
have access to the 24 by 7 tool access.
Okay, okay. And means for e-learning base, can we get that mentor based support for 3 hours from Monday to Thursday?
That I'm not sure. That
Okay.
I need to ask with respect to the admin. You can
Okay,
confirm
okay.
it with them.
Yes, yes. For e-learning mode only, I'm asking. Okay, sir.
Yeah, so that you can
Uh,
be able to confirm. Okay, let me see whether he is available. I'll ask
okay.
him to join. Just give me a minute.
Yes, yes, yes.
For e-learning, if we have any doubts, how we can to approach to you? Sir?
Hello.
Hello. Hi.
Yes, hello, sir. I just want to ask you that if I choose this e-learning mode to take this course, so can we get any mentor-based support like weekly once or twice? Is there any provision for that?
Sorry, I was away. Okay, so the admin side is kind of busy right now, is attending someone else. So you will be getting all the recordings. Okay, so you have registered, right? So you will be getting all that particular recordings of today's session, and also there will be one-to-one discussions with you. So all your queries you can be able to raise it over there. Okay, regarding to that e-learning lab support and how you can be able to let's say enroll, what will be the cost and everything, you can be able to discuss it over there.
Okay, sir.
Okay, right. So for those who have attended through the LinkedIn or anything, you can just contact the particular admin number, okay, such that he can be able to provide all that particular support where you have got it. Yeah, so all that materials and everything you can be able to ask during that particular one-to-one session. Okay, let me see. So please note down the number. His name is Manohar. Oh, okay, okay. Just a second. Introduction slide doesn't have major thing. Okay, you can contact Manohar for any other further if you haven't received any kind of responses. So it's just in introduction slide we have is like just basic of that I have explained mostly in. Okay. Yeah. Any other doubts? Okay. So I'm closing it for today. So you can contact Manohar and you can get all the particular details which you need. Okay. Thank you. Bye everyone. Have a great day.